In module 2 we have discussed about the multi-carrier concepts. So module 2 actually it shows that how the multi-carrier modulation is going to be happen and what are the differentiation between OFDM block diagram as well as OFDMA. So today we have one brief about the OFDM basis, that is nothing but orthogonal frequency division multiplexing. So this OFDM stands for orthogonal frequency division multiplexing. So if you are thorough enough in what is orthogonal, what is frequency division, what is multiplexing, then it will be very easy to understand the future logic. So actually orthogonal frequency division is nothing but it is a technology. Actually we are splitting a wide frequency band into many small frequencies and carry data onto each of the subcarriers. So a lot of subcarriers are there which are used to carry the data. Then first we will see what is frequency division. Okay, here the frequency band, wide frequency band will get divided into multiple number of narrow band frequencies, that we will call it as frequency division. Okay, so data on each of the subcarriers are transmitted simultaneously. So we can say this is the kind of multiplexing. In general we know one single message is multiplied is one to many output. So now one single frequency band or wide frequency band we are dividing into number of frequency bands. So we will call it as, and whatever number of frequency band we are dividing, and each narrow frequency having carrying some data. Therefore we will call that type of process as multiplexing. In frequency domain we are considering the sampling point. Okay, in one carrier which will have a non-zero value and another subcarrier have zero value. Okay, so it means that the multiple subcarriers will exist, all are independent and does not influence the others. These characteristics are called as orthogonal. And also this we are using fast Fourier transform to achieve a L radio frequency radios path in both the transmitter and the receiver. And also inverse Fourier fast transforms are able to create a multitude of orthogonal subcarriers using just a single radio. Now these all are the basic features of orthogonal frequency division multiple access. Now let us have a discussion about the transmission with God intervals. So we are using n number of subcarriers here, and we wanted to give some space to avoid overlapping or losing of information, all those things. So we are taking a T, capital T, that is the God intervals as T, that is equal to L into Ts. This L is nothing but we have divided. Our intention to is achieve LRF radio path. Okay, so here we are introducing a God time that is represented by TG between the OFDM symbol. Why we wanted this TG in the sense we want to make each OFDM symbol as a independent after going through the wireless channel. Now this is the symbol, see, OFDM symbol, and in between the two OFDM symbol we are giving a God time that is represented by TG, so that it will make each OFDM symbol is independent, so that interference will not be happen, it get avoided. And also delay spread, we already studied wireless channel parameters. There are 4 type of wireless channel parameters, that is coherence, bandwidth, coherence time, angular spread, delay spread, Doppler spread. Here the delay spread, which will be represented by tau, is playing a vital role here. So now coming to this, we will see cyclic prefix. Here cyclic prefix is the important parameter. So what is meant by cyclic prefix? So here it will act as a buffer region or we can say it is a God interval. For what purpose we wanted to go for cyclic prefixes? To protect the OFDM signals from ISA. We already aware about that. ISA is nothing but inter-symbol interference, and we have taken a elegant approach to make a communication link as a ISI free. Okay, the cyclic prefix will be obtained by considering some of the last samples. Okay, and it will be appended at the start of the symbol block. So each OFDM symbol to be independent for the purpose of avoiding the ISA and ICA. Therefore, we can say that the cyclic prefix will be in the order of two functions. Okay, the main function is nothing but it will provide a God interval to eliminate ISI from the previous symbol, and also the end of the symbol, that is a linear convolution of a frequency selective multipath channel, can be modeled so that it is transformed to the frequency domain via discrete Fourier transform. And this approach can be done in frequency domain processing, so the estimation and equalization of the channel can be done effectively. And here if you see the fast Fourier transform and the inverse fast Fourier transform algorithm are used to realize the OFDM, which will reduce the computational complexity. Okay, and in the IFFT operation, the transmitter allows all the subcarriers in the digital domain and thus requires only a single radio to be used, so that to create an ISI free channel, the channel must appear to be a circular convolution. So uh, we are going for the cyclic prefix. Now here we are adding a cyclic prefix. In the diagram itself you can see clearly the first block represents the transmitted signal, and the second frame is data payload, and third we are adding a cyclic prefix, and the cyclic prefix will be in the order of xl minus v to xl minus v plus 1, xl minus v plus 2, up to xl minus 1. So that like that it will be taken place, so that the OFDM symbol will be get separated by or independent with each other. Now if you come, cyclic prefix will be added to the transmitted signal, and then it will create a signal, that is y of n. The convolution is nothing but y of n is equal to x of n into circular convolution of h of n. Let us see how the circular convolution is going to be taken. So here maximum channel delay spread has the duration of v plus 1 samples. Okay, after that we are adding a God band of v samples between each OFDM symbols, and this independency will considered, and we can make how the OFDM symbol in the time domain with a length L vector can be represented. That can be given as capital X is equal to x1, x2, x3 up to xl in the vector formula. After applying a cyclic prefix of length, the actual transmitted signal is remodified along with the cyclic prefix code. Already we told that we are adding the cyclic prefix. That is, in this we can see that xl minus v into xl minus v plus 1 up to, and original data is nothing but x0, x1 up to xl minus 1. Now coming to the output of the channel. So this output of the channel is given by the definition that it is CP is nothing but cyclic prefix output, that is equal to H into XCP. XCP is nothing but after applying a cyclic prefix length, what is the actual transmitted look like. So that we have seen in the above expression, that is we have combined the cyclic prefix code as well as the original data. Here what is H? Everybody will get a question that we are including a factor called H. This is the length that we have already mentioned, that v plus 1 vector which will describe the impulse response of the channel during the OFDM symbols. Now, the output of the cyclic prefix, that is YCP has samples. So, what formula or what way we can do it? It is nothing but length of the OFDM symbol, okay, plus length of the channel response minus 1. So that length of the OFDM symbol is capital L plus V, right? Length of the channel response is V plus 1 and minus. So we will get L plus 2V samples. Now we wanted to do the circular convolution operation, that is nothing but y of n, that is equal to x of n, a circular convolution of h of n. So due to the cyclic prefix, we know that y naught will depends on x naught and the circularly wrapped values is xl minus v up to xl minus 1. We can see y naught is how it is happening. Y naught is equal to h naught into x naught plus h1 into xl minus 1 plus up to hv into xl is equal to 1. This is the matrix. If you put, we will get the circular convolution as already we have done in the processing technique called digital signal processing. So this is the basic OFDM basics, and now it is we have put in the circular convolution format starting from x of n, then h of n minus l minus 1, then h of n minus. So what the circular convolution is shifted like that, it has been seen in the diagrammatic picture very clearly. Hope everyone has some idea with the formulas, mathematical expression, as well as this diagrammatic concept. Now, here the rate loss or power loss is very important, because we have introduced a God time which is called as TG, right? That will separate the each OFDM signal to make the ISI free communication link. So now at last now we wanted to check the rate loss, or we will call it as power loss. So the formula for is given as the use of cyclic prefix entails data rate and power loss for the both, that is rate loss equal to power loss, that can be defined as L divided by L plus V. Okay, so hope everyone understood what is orthogonal frequency division multiplexing. So you may explain, or you may have an entire deep idea about orthogonal, what is frequency division and what is multiplexing, for what purpose we are doing the introducing a God time here, and for what purpose we are introducing a cyclic prefix and all those things. Hope everyone understood clearly, and thank you.